Thank you for coming to this presentation of nanoHUB's open access cloud computing resources for nanomanufacturing, nanobio, and data science. I'm Dr. Tanya Faltens, the Educational Content Creation Manager for the Network for Computational Nanotechnology at Purdue University. We will start with an introduction to the Network for Computational Nanotechnology and nanoHUB. Then I'll tell you about an exciting upcoming undergraduate research opportunity that you and your students may be interested in. The bulk of this presentation will be showing you examples of some nanoHUB resources that you might find useful. My goal here is to interest you enough to click on some of the links to take a deeper look. I hope that something that I show you today will spark your interest and be relevant to your teaching. Importantly, there is a link to a form at the end of this presentation that you can use to request more information and free training. At the Network for Computational Nanotechnology, or NCN, we believe in equity and access and have worked hard to make cutting-edge technical content, high-performance computing power, and high-quality educational material openly available. NCN has been providing open access simulation tools to worldwide users since 2002, when we were the first to provide research-grade computational simulations in the cloud on our cyber platform known as nanoHUB. 10 years later, we were one of the first to host a massive online open course, or MOOC, in our Classrooms Without Borders effort known as nanoHUB U. Over this image of NASA's world at night, you can see red dots that represent people using nanoHUB educational resources and yellow dots that represent people running nanoHUB simulations. Night or day, nanoHUB is always on, and in the last year we have reached 2 million people in countries all around the world. We continue to innovate and add powerful new features to nanoHUB. In 2020, we were an R&D 100 winner in the Software and Services category. The Network for Computational Nanotechnology is currently made up of 3 nodes, each with separate funding from the National Science Foundation. The NCN Cyber Platform node is responsible for the support and development of the nanoHUB infrastructure and is located at Purdue University. The NCN Engineered Nanobio node does research on computational simulations for biological applications and is located at Indiana University. The NCN nanomanufacturing node does research on simulating the steps in nanomanufacturing processes and is located at the University of Illinois at Urbana-Champaign. We are presenting here at HiTec because all 3 NCN nodes are partnered with the Nanotechnology Education Center. We will be supporting undergraduate research experiences for community college students as part of their MNT Collaborative Undergraduate Research Network, or MINT-CURN, using the nanoHUB cyber infrastructure and cloud computing capabilities. If you would like to get more information about this research program, please fill out the form at the end of this presentation. You can access nanoHUB and all of its resources by going online to nanohub.org. nanoHUB offers free educational content that includes full courses and ready-to-use lessons, free online simulation tools, many of which are used in research, and a large community that includes online support. I'm now going to give you a brief glimpse of several nanoHUB resources that you can explore in greater depth by following the links in the slides. We have a new series titled Getting Started in nanoHUB, which you can access via this URL in the slides, nanohub.org/resources/35248. This resource will help you set up your free nanoHUB account and access various nanoHUB functionalities. One of the areas in nanoHUB where you may find relevant resources is the Nanotechnology Workforce Development Group. In this group, you can find links to content in nanoHUB created by the Nano ATE centers. These include MNTEC MinTech, or the Micro Nanotechnology Education Center, the NAC Network, NanoLink, NIATech, or the Northeast Advanced Technological Education Center, the Support Center for Microsystems Education, or SCME, and SHINE. Let's take a look at the SCME resources. As I scroll down the page, you'll see that they have a number of resources. I won't go all the way down the page, but this first set on MEMS fabrication has student resources on the left and instructor versions on the right. Another resource that may be of interest to those of you in biological areas is the nanoHUB U course called Biological Engineering Cellular Design Principles. In this course, you will explore both established and emerging cellular design principles and learn how cells function as the basis for cellular engineering. Let's take a look at part of the intro video.
Welcome to the nanoHUB U course, Biodesign, Cellular Design Principles. I'm Jenna Rickus, Professor of Biological Engineering and Biomedical Engineering at Purdue University. When you think of cells, you probably think of images like these of neurons, plant cells, and fibroblasts. But do you think of images and words such as information processors, oscillators, molecular factories, or sensors? In this class, you will. This is not a cell biology class, but rather an engineering class, where we will apply engineering principles such as thermodynamics and kinetics to understand and design the function of cells. Once you start to view cells in this framework, you'll start to see cells as microdevices. You'll think of the photoreceptors in your retina as organic single photon detectors. And you'll now see new ways to re-engineer and design cellular microdevices, as well as engineer non-living devices inspired by biology and nature. You'll also have a new tool set for engineering microdevices to interact and communicate with cells, such as this microchip designed to monitor plant cells in space, and this tissue-engineered brain mimic designed to study brain tumors.
You can introduce your students to coding using Jupyter Notebooks installed in nanoHUB. These notebooks run in the cloud, so you can access them via a web browser and no installation is required. In addition to the Anaconda installation, many additional libraries and packages are already installed in nanoHUB ready for you to use. For beginners, there is a resource on getting started with Jupyter Notebooks in nanoHUB, which is shown in the link on this slide. The lessons include both PDF handouts and video instruction and cover the following topics with more to be added. Learning Python 3 using Python for Everybody with nanoHUB Jupyter Notebooks. Setting up your nanoHUB file structure in Jupyter Notebooks. The Jupyter Dashboard, Notebook, and Terminal interfaces in nanoHUB. And running a Python 3 script in nanoHUB Jupyter Notebooks. Some familiarity with Jupyter Notebooks is helpful for these data science resources. On this page are a couple instructional resources designed to teach data science concepts. The first tutorial introduces some modern data exploration and visualization tools. The first link, Introduction to dplyr, ggplot2, and other tidyverse friends, modern tools for data exploration and visualization, is a video of a recent webinar training session. The second link, Tidyverse Data Science Tools for STEM Applications and Datasets, is the associated tool in nanoHUB. This introductory level tutorial uses the R programming language and introduces the Tidyverse family of tools, which are powerful tools for data cleaning, analysis, and visualization that can be used across many STEM fields. I encourage you to take a look. The machine learning modules teach data science and machine learning techniques using Python and several Python packages that are installed in nanoHUB. There are 6 modules in this set. Each includes a video, a tutorial using a Jupyter Notebook in nanoHUB, and suggested exercises for practice. The first module discusses the FAIR data principles, which are important for sharing data, for example, laboratory data, in order to make it findable, accessible, interoperable, and reusable. As machine learning takes a larger part in scientific workflows, technicians will increasingly be tasked with cleaning and uploading data into database systems. The subsequent modules in the series introduce several machine learning techniques applied to material science datasets. Now we'll take a look at the nanomanufacturing group in nanoHUB. The vision of the nanoMFG node is to simulate every step of the manufacturing process of a nano-enabled product. You can see the nanomanufacturing group at this URL, nanohub.org/groups/nanoMFG. One of the nanoMFG resources is this tutorial series that provides extensive video instruction on their graphene rescue platform. They are creating a database of graphene recipes for synthesis of high-quality materials, including an introduction to cloud manufacturing. The video tutorial discusses both how to manufacture and characterize graphene and how to use their simulation tool. And this URL is nanohub.org/resources/35081. The NCN NanoBio node develops a powerful set of integrated computational tools that span the range from nanoscale particles to cellular scale structures to tissue scale morphologies. You can find the NanoBio group in nanoHUB at nanohub.org/groups/nanobio. I'll now show you a few of the NanoBio simulation apps that are built on the CompuCell 3D and PhysiCell frameworks. These frameworks allow users to set up simulations of cells interacting with one another and with their environment. Specific systems are published in nanoHUB as apps and have simplified control panels to allow users to explore the effects of changing a few key parameters. Some faculty use these apps in their undergraduate teaching. If any of these apps look interesting to you, be sure to let us know in the response form at the end of this presentation so that we can notify you of upcoming workshops and connect you with training resources and individual support. The first example apps are built on the CompuCell 3D framework. CompuCell 3D is a flexible, scriptable modeling environment that enables users to construct simulations of many multi-scale, multicellular problems, including angiogenesis, cancer, the immune system, and tissue engineering. The chemotactic elongation demonstration showcases the use of cell elongation with chemotaxis, which is the movement of cells in response to a chemical concentration gradient, for angiogenesis, which is venal formation or the formation of capillaries. In this simulation app, the user can adjust 3 key parameters: the target cell aspect ratio, the energy associated with the aspect ratio, and the strength of the cell's movement up a chemical signal gradient. Let's take a look at this simulation in action. So first I'm resizing the windows so that there's more space to see the smaller windows. And I'm going to stop the simulation, which is running from the beginning, increase the size of the inner simulation windows. And here we see that there are 2 graphics windows, a steering panel, a model editor, and a console. And I'm going to move these, and a cell type colors panel. So I want to move these out of the way. So I'm clicking on the corner and then clicking down at the bottom to put these windows away, just to make a little bit more space to see these frames. Okay, so here I'm going to swap these around. So I'm going to make this first panel show the cells, and the second panel, okay, I'm going to make the first window show the cells, and the second graphics window show the concentrations of chemicals. So that will just take a moment to update. And the steering panel shows those 3 parameters that we can adjust. The first one, when the target length is 0, that means that the aspect ratio will be pretty much like a circle or a square, and on the other extreme you'll have an elongated cell. So I'll just leave this at the default value. The second parameter adjusts the strength with which the cells adopt the target length. So with a lambda of 1, the cells will be at the target length, and with a value of 0, then there's little energy associated with the cells having the target length. And the final parameter adjusts the strength of the cell's movement up a chemical gradient. So for cells to move strongly up a gradient, you make that a large value, and for them not to be affected by a gradient, make that a small value. So the initial values are all zeros, so that there is no elongation of the cells, no real drive for the cells to be elongated, and the cells do not strongly move in a chemical gradient. I'm going to click the second button to initiate a new simulation with those parameters, and hold it steady. Again, I would like to close these windows to make a little bit more viewing space. Let's see if I can put these away. And close the console. Great. So here we have, I have to reset these again. So here we have the simulation ready to go, and I will click on the play button to start the simulation. So with each time step, we can see in the bottom corner the Monte Carlo time step, and every 10 time steps the images update, and you can see that this concentration gradient shows that the cells are secreting a chemical signal, and that signal, the chemical, is accumulating in the area around the cell. It's important to note that this chemical degrades quickly when it's in the extracellular matrix, because this chemical works when there's a strong gradient and there's not going to be an accumulation. As this simulation progresses, we can see that the cells are moving around a little bit. You see a few cells starting to stick together. There's a small advantage to cells adhering to one another, but there's not really a strong drive for the cells to move a lot or change shape. So I'm going to pause this and change some of these parameters. So let's make the target length quite large. So this is going to be an elongated cell. And let's make the lambda length quite large, the maximum, so the cells will strongly want to adopt an elongated shape. And let's also make the lambda for chemotaxis very strong, so the cells will now move more quickly when they are experiencing a chemical gradient. And then I will continue the simulation from here, and we'll see how the results look different from before. So almost immediately you can see the cell shape has changed. And it doesn't take very long for cells to start connecting up with one another, and you can see how this can lead to the formation of networks that span across the whole simulation area. The next example is the COVID-19 virtual tissue model for tissue infection and immune response dynamics. This simulates tissue and immune system interactions during a viral lung infection. On the left, you can see how the infected cell field, virus field, and chemical concentrations evolve over time during the simulation. This next example shows a green macrophage hunting a blue bacterium through a maze. The bacterium secretes a diffusive chemical signal that the macrophage detects. By moving along the gradient of this chemical signal, the macrophage can hunt the bacterium. The next three example apps were created with a PhysiCell simulation framework. PhysiCell simulates large systems of cells and 3D tissues, including the biochemical microenvironment, the stage, and many mechanically and biochemically interacting cells, which you can think of as the players upon the stage, enabling users to study how cells move, grow, divide, interact, and die. Tissue scale dynamics emerge from these systems of many interacting cells as they respond to and influence their microenvironment. The first example simulates a cancer nanotherapy, where users can design nanoparticles that are conjugated to novel cancer therapeutics. In this app, users can simulate the growth and migration of cancer cells in the tissue environment, as well as the pharmacodynamic response to user-designed therapeutics. The second example demonstrates how simple rules for chemical and contact-based communication could be used for active delivery of therapeutic compounds while overcoming traditional biotransport limits and using hypoxia to target delivery. In this app, the cancer cells are shown in green, worker cells are shown in red, and actively transport blue cargo cells that kill the cancer cells. The third example is a model that simulates replication dynamics of SARS-CoV-2 in a layer of lung epithelial cells. The blue cells are uninfected. As the number of virions in the cells increases over time, they turn brown and then yellow. When the cells die, they are shown as black and then are removed from the visualization. The simulation app allows the users to explore how different parameters affect the course of the infection. While these simulations were developed for research, they can be used by undergraduate students to explore the nature of many cellular and tissue-level interactions. I hope that some of the examples you have seen have piqued your interest. Please explore the links shared in this presentation. We are happy to help you get started using nanoHUB resources in your classes. Please let us know your interests and request more information or training by filling out the Google form. I would like to thank the National Science Foundation, EEC 1227110, for supporting the Network for Computational Nanotechnology and my work. Any opinions, findings, and conclusions or recommendations expressed in this material are those of the authors and do not necessarily reflect the views of the National Science Foundation.